Alright, so we want to talk about chemical kinetics. I just want to introduce you to chemical kinetics and the chemistry that you'll be doing in second semester. I know last semester, for some of you were around, I think it was just videos we were giving you. Now this time around we're available for you. So expect these classes as often as you can. Okay. So this was a 2023 exam paper for second semester. So it's called Chemistry 1112 and this was section A, as you can actually see. So section A requires you to answer all the questions, and question one was directly from chemical kinetics. You can see the question. Whenever you see anything to do with rate calculations, rate expression, rate of formation, the K, this deals with chemical kinetics. So I just want to show you some more questions before, so that you see that this topic is very, very important. Okay. Of course, if you check on the next one, this is coming from chemical equilibrium, which we'll also talk about. Uh, F3 is coming from solubility equilibrium. Ka, this is also coming from acid base equilibrium. Um, F5, that's also coming from phase equilibrium. More fraction, partial pressures, so that's also phase. So we can usually call it, if you want, you can call it solutions and their properties combined with phase equilibrium. Then if you look at A7, what happens to the equation when if A is increased? This is also chemical kinetics. So at the end of this lesson, you should be able to answer this. No, this is actually, no, this is chemical equilibrium actually. So it's chemical equilibrium. Sorry. Sorry, this is coming from Chateaubriand's principle. Organic chemistry. If you go to section B, question one is compulsory. And what is the question saying? So you can see sorbate products. So that's coming from sorbate equilibrium. It's a very simple topic that we'll do after kinetics. We'll do chemical equilibrium and then connect to solubility equilibrium. Now, B2 again. This is again a full question on chemical kinetics. Rate constant, order of the reaction, half-life, how long, what time. Again, question repeats. And then this is coming from also, it's also the same topic. Okay, chemical kinetics. We call it the Arrhenius equation. That's where that question is coming from. Now, if you look at these marks, I think they should add up to 20 marks already, plus the questions we've left in section A. So that's over 20 marks of a paper. And so you'll see that this topic is very important. So there are quite a few number of topics that we're going to cover. And the good part is you cover them actually before you actually get to first submit your assessments. Okay. So my name is Bishonga. In case you're wondering what my name is, I'm sure most of you are familiar with Isaac. So Isaac. So Bishonga is my name, and I'll be taking in chemistry. And I prefer to teach calculus, so I'll also teach you calculus and mathematics. Okay. So what is chemical kinetics now? This simple topic that we want to go over. So, as you might guess, the word kinetics deals with speed, right? Kinetics. So, in simple terms, I like defining chemical kinetics to be the study of, so you can say rates of reactions and their mechanisms. So you just don't end on looking at the speed, because I believe you understand that whenever you're talking about the rate involves the time aspect, right? How long it took for something to actually happen. That's what the rate is. So the study of rates of reactions and their mechanism. Okay. So actually, full say reaction mechanisms. What basically happens for that reaction to actually proceed? That's what chemical kinetics is concerned with. Just these two things. So I don't allow questions yet because we've just started. So I'll repeat what I've said. I'm sure you understand it in another way. Mm, unless if you can't get what I'm saying. Are you getting me? Okay, great. So, what reaction? If I talk about a chemical reaction, what reaction are you able to think about? Okay, let's think of a simple reaction between hydrogen and nitrogen. They all exist atomically. So, if these two react, what can they give us? Okay, let's just imagine it gives us ammonia, right? And of course, we're not interested in balancing because all these equations will be balanced for us under this topic. So, how would we balance this? I think we can add a 3 there, and then if we add a 2 there, that's balanced. Okay, so if you look at this reaction, chemical kinetics is concerned, firstly, want to determine how fast the reaction proceeded. That's number one. Number two, under chemical kinetics, we are also concerned, want to know how the reaction actually proceeded. So we call that reaction mechanism. Okay. So there are other few things again that we'll also be interested in that are related to the rates. Things like the order of the reaction, things like the half-life, things like the time. Okay, and then when you go to Arrhenius equation now, Arrhenius equation requires you to, in fact, there's one important component I've left. There's also the constant K. Okay, the reaction constant. So let's try to break it down now. Let's try to see certain things here. Um, so that was just theory. Okay, now the rate of the reaction can be determined in terms of the reactants. So you understand what's on the left are the reactants, right? That's very basic. And then what's on the right are what? The products. So if somebody was to ask me to determine the rate of this reaction, if I'm given the information about hydrogen, nitrogen, or ammonia, any of the three, giving me one of them is enough for me to determine the rate of the reaction. Okay, how would I determine the rate of the reaction? Let's try to take an example. Let's say they gave me information about nitrogen, right? They gave me a table that was observing the time against the concentration. Okay, so if you see square brackets, just know that what that is representing what? The concentration. So the concentration of nitrogen. So let's say initially when you started the reaction at 0 second, the concentration of nitrogen was 2 molar concentration. After 2 seconds, it was 1 molar concentration. After 4 seconds, maybe you can say 0.8, or maybe, yeah, or maybe 0.4. In fact, basically, let me say 0.6. So that's just like trying to give you an example. Okay, so this is information about nitrogen. So how would we determine the rate of the reaction based of that simple data there? So as you might guess, the formula is the change in the concentration. In this case, we're talking about nitrogen over the time it took. Now I know that's what you're thinking, but we have to add extra information. So under chemical kinetics, things like the coefficients do matter. Okay, so for the sake of demonstration, let's assume there was a 2 in front of nitrogen. Don't go and say no, I didn't balance the equation properly. Let's assume it's an assumption. Let's say there was a 2 there for demonstration's sake. So it would be 1 over the 2. But in a case where it was just like there was just a 1, this is not even necessary. It can just be 1 over 1, which doesn't make any difference. Okay, now some of you would actually already observe to say, if we are to use that piece of information and substitute, of course for the change in concentration it's a final minus the initial, so you would get a negative, right? So to avoid that, since we know that the concentrations of reactants as you can see, they are reducing as time progresses, right? As time proceeds, they are reducing. So we'll add a negative whenever we're calculating the rates using the reactants to ensure that our rate is always a positive result. Okay. I've talked too much. Let's now calculate. So negative half, the change in concentration would be as simple as, let's just use the first and the last part. So 0 0.6 minus 0 minus 2, yeah, and then divided by the time. That was the final time was 4 minus the initial 0. Okay, that's enough to give you the rate of the reaction. Now, as you might guess, on top we have the concentration, which is molar, the time, in this case, let's say it was in seconds. So the units are going to be molar per second. I hope you've come with calculators. 0 0.6 minus 2 is what? Negative 1.4. What are we getting there? Okay, I'm not so interested in the answer anyway. I'm not so interested in the answer. So let's assume the answer was 0 0.4. If somebody's calculated, will help us with the answer. But let's say that's the answer. That's how we determine the rate based on the information of nitrogen. And I'll give you some sample data. If I was to give you information about the two reactants and the product, it doesn't matter what you choose to use when doing your calculation, the answer will still be the same. Okay? So that's how we determine the rate of the reaction. This is just a basic introduction. Yeah. And that question actually does come. Okay? Very often. Is there any question before I get to the factors that affect the rate of the reaction? Any question? I saw some hands when we started. Or if you've understood, just make a comment you've understood so I proceed. Feel very free to unmute yourself and tell us your query. Are we good?
Yes, we are.
Okay, okay. I think this is something basic now that I'm moving to, that I'm moving on to. Um, what are some of the factors that you think affect the rate of the reaction? If you add a reaction, or if you are performing a reaction, what are certain things that you think would affect the rate of that reaction? What would make it faster? What would make it slower? hmm Okay, somebody says temperature, concentration. Okay, that's fine. Anything else? Concentration, temperature. Okay, can talk about surface area. Okay, that's also given. Mbutwana, thank you for that. And then we can also say, I think surface area and size of molecules are the same. Um, and then we can also talk about pressure in terms of gaseous reactants. Um, what else can we talk about? Okay, I think these four are enough, but of course, things like use of a catalyst as well can affect the rate of the reaction. So we'll limit our answers to the five. Okay. Now, what am I trying to say? So, for you to understand how these factors affect the rate of the reaction, I know you understand the basic idea to say if you increase the temperature, the rate of the reaction does what? I know most of us you did this in biology back in high school, and even in chemistry for some of you did chem did 50 70, I don't know, something like that. So now tonight I want you to understand why is it that if you increase the temperature, the rate of the reaction does increase as well. You should be able to give a proper explanation for that. So two things that you have to understand. Number one, there's what we call collision theory. Kindly mute yourself. Who is that one who is making noise for us? Anyway, let's proceed. So you should be able to understand what collision theory is for you to give a proper explanation for the reasons why these factors affect the rate of the reaction. So collision theory tells us to say for a reaction to proceed, okay? For a reaction to proceed or for it to occur, for it to happen, what happens? Particles of the reactants, okay, must collide. Not only should they collide, but they must collide with sufficient, okay? That means enough, okay? As simple as that is. For a chemical reaction to proceed, particles of the reactants must collide with sufficient energy. Let's break that down. What are we trying to say here? So if we go back to our example, nitrogen and hydrogen reacting, okay? For this reaction to actually give us the ammonia that we want, the requirement is that the particles of nitrogen and hydrogen must be in contact. That's what we're trying to say. The reaction can't happen minus these particles of the two reactants being in contact. Now, not only should they be in contact, they should collide. Okay? Not only should they collide, they must collide with sufficient energy. Okay? That's the principle of, or that's the theory of collision theory. Okay? So, ideally, for a reaction to proceed, it must be something that should come out like this. If these are the particles of hydrogen, the particles of nitrogen on the other hand should be a mix up so that they are in contact. Okay, so the particles, we understand particles are very tiny. Okay, so they must collide with one another for the reaction to actually give us one substance, ammonia. Okay, that's the principle there. So based off that principle, and if we build it up, let's start with concentration. When you increase the concentration of the reactants, what are you trying to do? You are increasing the probability or the chances of the particles to do what? To collide, because there are more. That's what concentration is. If you increase the concentration, you are increasing the chances of the particles to collide. Okay? So, in short, the higher the concentration, the higher the what? The rate of the reaction. Why? The principle is very simple. If you increase the concentration, you are increasing the chances of the particles of the reactants to what? To collide. As a result, the rate of the reaction is higher because particles are colliding more. So if you see now how we are reasoning based off the collision theory that I just gave you. Mhm. Are we together?
Yes, we are.
Any question or any contribution?
I think everything is okay so far.
Everything is okay so far. Okay. Number two, let's move to temperature. What happens when you increase the temperature? The rate also does what? It also does increase. Why is it so? So we on top of the collision theory, we can also introduce the kinetic theory. I believe most of us already know what kinetic theory states. It's the first thing you learned in grade 10. Kinetic theory of matter. No, so matter is not about small particles, and these particles are always in a constant random motion, and then there are frequent collisions between the molecules and whatnot. Okay, but let's forget about all that and try to simplify it. In terms of temperature, so under kinetic theory defines temperature to be the increase. Temperature is defined as the increase in the internal kinetic energy of what? Of the particles. Are we together? I'm defining temperature to be the increase in the internal kinetic energy of the particles. So what that implies is if you increase the temperature, you are increasing the speed because kinetic energy is the energy that is concerned with the movement of particles, right? So when you increase the temperature of the reactants, you are increasing the kinetic energy of what? Of particles. Now, if you increase the kinetic energy of the particles, that's leading to what? How many of you agree to say if particles are moving faster, the chances of them colliding are actually higher, right? Now, not only are the chances higher, but even the energy. You remember we said under collision theory to say for a reaction to proceed, first of all, the particles must collide, but with sufficient energy. So the temperature also contributes to the energy and to more collisions. So more successive collisions and sufficient energy provided. So the rate of the reaction does what? Proceeds based on that very simple principle. Okay? So I've reasoned based on kinetic theory, saying to say if you increase the temperature, you're increasing the internal kinetic energy of the particles or the reactants, leading to more successive collisions between the reactants, and hence the rate of the reaction increases. The opposite is true. Reducing the temperature reduces the kinetic energy of the particles. Particles will be moving slower, and less collisions will occur, and the rate of the reaction will reduce. Reducing the concentration as well, if you go back previously, you can apply the same principle to actually give a reason. Okay? I think I've talked too much. Too much theories. So theory is enough, right? So now let me give you this. Let me allow you to now just come in and talk a bit. So we talked about surface area, we talked about pressure, and then talked about the catalyst. Okay. So feel free to unmute yourselves and try to give a reason. What would happen if to increase the surface area? What would happen if we were to increase the pressure? Just comment on one and give a chance to your friend to comment on the other. Of course, we can't say increase in catalyst. Doesn't make sense. Use of a catalyst. What would happen if we were to increase the surface area of the reactants? Anybody? Like it seems we're still not willing to talk, so I'll just explain. How to explain surface area? So something that might interest you is the fact that um, when you look at crystallized particles, there's a salt, um, crystallized salt, that should be something like that, compared to the one that is not crystallized, which is like in blocks. The one that is crystallized has actually a higher surface area. Okay, this one has got lower surface area. What that implies is the contact between the particles is actually lower for this, the one with lower surface area. The one with higher surface area, the point of contact is actually higher. So what's the principle here? If you increase the surface area of the particles, the chances of contact are higher. So the rate of reaction does proceed when the surface area is higher. Okay? So it's not a good idea for you to get blocks of your reactants if they were in solid form. Get the blocks and put them together. The reaction is going to be very slow. But if you are to increase the surface area by probably breaking the particles into smaller ones, you're increasing the surface area and there would be more contact and more collisions between the particles, leading to a higher rate of the reaction. Okay? Simple principle. Simple principle. Okay? So if you're not understanding some of these things, don't worry, I've got videos that have already explained this, and we'll look at several questions together that will help you to remember eventually. Okay? And then on the pressure part, some of us already know to say pressure is actually inversely proportional to volume, right? So I usually like using that concept to explain pressure. If you increase pressure, of course, the rate as well is going to be higher. So let me give you this basic example. Look at the two containers, container A and B. Let's say we had added the same number of particles, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, 1, 2, 3, 4. Where do we have our pressure? Is it in A or B?
A.
So where would you expect the rate of reaction to be higher? Is it in A or B? Don't forget about collision theory. So where do you expect to have more collisions? Is it in A or B? Hmm. Anybody can respond to that. Where do you expect to have more collisions?
A.
Okay, so in A we would have more collisions actually. So the higher the pressure, the higher the rate of the reaction. Because when the pressure is higher, there are more collisions between the particles. And then use of a catalyst. What happens when you use a catalyst? Is the reaction faster or slower?
It's faster.
So catalyst has got to do with there's what we call now activation energy. Activation energy is the minimum energy required for a reaction to proceed. Remember from collision theory we said particles must collide with sufficient energy. That sufficient energy is what we're calling the activation energy, right? So a catalyst, what a catalyst comes to do is it does reduce the activation energy, meaning that less energy will be required for the reaction to proceed, hence it will be faster. That's what the catalyst does. You don't say the higher the catalyst. No, 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 no. It's either you're using a catalyst or you're not using it. So we say the use of a catalyst does lead to a higher rate of the reaction. As basic as that sounds. Okay. I'll take you back to what I've already told you. The same reaction balanced is this is How is it hydrogen 3? So 2, 3, 2. Okay, yeah. So the rate of the reaction for that equation can be summarized as, in terms of nitrogen, it would be negative change in concentration of nitrogen over the time it took. It's also equivalent to negative 1 over 3 change in concentration of hydrogen divided by the change in time. And then that's also equivalent to 1 over 2 change in concentration of ammonia divided by the change in time. So you will notice that actually for ammonia I'm putting a positive there because when a reaction proceeds, actually what basically happens is the reactants will be reducing, the products will be what? Increasing. So implying that for the product, if you had started with 0, as the reaction proceeds, it will be increasing, so it may even increase to 2. But on the other hand, for the reactants, they are going to be reducing. So that's why we're adding negatives to ensure that we get positive answers for the left and the right hand side. Okay, that's for the rate of the reaction. Are we together? So this plus the factors is what you've learned tonight. Now let me add something little to that. Um, so it's something that's very interesting actually. So we call this differential let laws. Okay. So next time we're going to talk about let laws in the cases where they give you, let's say experiment 1, experiment 2, and experiment 3. Let's assume for the first experiment they tried using 1 molar concentration of the reactants, and then in fact they only give the reactants, they don't give the products, and then they'll put the last column for the rate, they'll call it the rate. Okay, so let's say they say the rate for the first experiment was measured to be 2 molar per second. In the second experiment they decided to double the nitrogen concentration and maintain the one for hydrogen. They observed that the rate was twice, and then for the last one they did the opposite. They maintained for nitrogen and doubled the one for hydrogen, yet the concentration remained the same, or the rate remained the same. So for such a question, they would ask you now to determine the rate law. The rate law is just an equation that tells you or that shows you the relationship between the rate of the reaction. So it can be something like the rate is equal to K and then based off the reactants. In this case, we add hydrogen and nitrogen. So you may find that what you'll be required to do is to find the powers of x and y. That's what you do for this kind of a question. So next time I'm going to show you how you can find the rate law of such a question, and how you can find the powers of x and y, and how you can also go on and also find the value of k. Okay, then the other part will be the integrated laterals now, where we have the zero order, the first and the second order of the reactions. Okay, so you don't want to miss out on this, and if you basically go back to our questions, you basically begin to see certain things that I've actually mentioned, right? For example, based off that question where we find where you're determining the lateral, that's where we'll be able to handle this question. Okay, and then from the integrated laterals, that's where you'll be able to handle the half-life part as well. Okay, and then after we're done with those two parts, that's when we'll now move to this part. This will be the last part of the topic, and we'll be done. Okay, so I don't want to give you a lot of information tonight, um, but if anybody has got a question, please feel very free to let me know just now. Any question from anybody? Or if you don't have any questions, I'll just go on and show you what you actually have access to on the site on the same topic. In case some of you want to take an extra step and be a little bit ahead of us, you're actually at liberty of doing that. So I think I'm not logged in. Let me just log in. Okay. So this is our site. So if you're registered for chemistry, um, so you only access the topics that are applicable to you. So if you've already done them in semester one, you can ignore the other topics and go directly to chemical kinetics. So you can see that all the topics that you are yet to learn are all actually already here, all the way up to organic chemistry. So if you open chemical kinetics, you see what I've already covered. I've covered the introduction, I've covered the collision theory and the factors, I've covered reaction less determination, and then this part I haven't covered it. Electrodes I'm yet to cover it. So everything that you are seeing in that exam paper is already available on the site. Okay. So this is what you have access to at your own convenient time. And yeah. So is there any question from anybody? This was a trial for chemistry that you are looking forward to. So for those ones who want to register tonight, you can just pay 70 kwacha instead of the 80 kwacha that we actually charge for chemistry and any other course of your choice. That's just valid for tonight. Yeah. And I think we'll end here. If there's any question, you can go on and ask before I end the meeting. Any question? Okay, you people are not talking, so it seems everything is fine, right? Okay, so go on, Mishek. I think I've seen a hand.
First of all, I would like to appreciate you, sir. That was well explained, and we managed to understand the concepts. So, my question, I would like to know: is there an arrangement like no, like myself, I subscribed, and I'd like to know if at all there is an arrangement whereby we'll be learning, because yeah, the way you teach is actually giving me that hope that you say I'll start with semester two at a good pay.
So is there any option for what, sir?
Like the arrangement maybe like on daily basis, or maybe per week, maybe or maybe twice per week, something like that.
Oh yeah, yeah. So your timetable will actually be out. So we'll actually be meeting twice in each course, but we'll be meeting almost every day for since we've got 4 courses. Yeah. And of course we'll give you some quizzes that, yeah, we've got some quizzes for you as well to just ensure that you're paying attention to what we're teaching you.
All right, sir. Thank you very much for that timely feedback.
No, okay, okay. Any other question? Okay, so I'll open the group. If you've got more questions, you can ask on the group.